Okay, so hello everyone. In this video, we will cover paging, TLB and segmentation. So in this video, we will first discuss about multi-level paging, inverted paging, and then translation lookaside buffer, TLB, and then a very important topic which is segmentation. These topics are very important and question always asked in exams like GATE, UGC NET, and even in your university level exams. So let's start with introduction to multi-level paging. Moving forward to multi-level paging. I have already explained simple paging in previous video. You need to understand what is paging, how we make page tables, what is page table entry. If you know all these concepts, it will be easy to understand multi-level paging. Now let's start. First, let's discuss why we need multi-level paging. When we already have a page table, why did we divide the page table into further multiple levels? What was the reason? The answer is simple. If the page table size becomes bigger than the frame size, we have a problem. Frame size refers to the frames in main memory where we store page tables. When we search for any particular page in a frame, we need the help of the page table. So we store the page table in one of the frames of main memory. If our page table cannot fit in the main memory because the page table size is large and the main memory's frame size is small, we obviously cannot fit in the single frame. Therefore, we have to divide the page table into smaller pages. Now, moving forward to inverted paging. Now, let's discuss inverted paging, which is completely different from normal paging. In normal paging, we create separate page tables for each process. Every process has its own page table that maps its page to frames. When the CPU asks for a page, we first consult that process page table to find which frame contains the requested page. For example, if we have 10 processes running, we maintain 10 separate page tables. If pages from the 10 processes are in the main memory, all 10 page tables must also be in the main memory, consuming valuable frame space. The main issue is that main memory is limited. If we have limited frames and we are using some of those frames just to store page table instead of actual data, we are wasting precious memory space. Now, inverted paging solves this issue by maintaining only one global page table for entire system. It is managed by operating system. Instead of having 100 page table for 100 processes, we have just one inverted page table. This table has as many entries as there are frames in the main memory. The key difference is in the table structure is normal page table indexed by page number contains frame number. Inverted page table indexed by frame number contains page number and process IDs. If main memory has 1024 frames, the inverted page table has exactly 1024 entries. Each entry in the inverted page table contains page number and process ID. We need both because multiple processes can have pages with the same page number. For example, process P1, P2 and P3 might all have page number 1, but they are different page number belonging to different processes. Now, when the CPU requests page 1 of process P3, then we search through the entire inverted page table linearly. We look for an entry containing page number is equal to 1, process ID is equal to P3. When found, the index of that entry gives us the frame number. Now, moving forward to advantages and disadvantages of inverted paging. In advantages, the first is significant memory savings, only one page table regardless of number of processes, and second one is better memory utilization. But disadvantage is what? Linear search time. We must search through the entire table to find entries, slower than normal paging due to search overhead. This is why inverted paging wasn't widely adopted. While it saves memory, but it increases search time. Now, moving forward to translation lookaside buffer, TLB. Let me explain TLB, translation lookaside buffer. The story starts with paging. In paging, we divide process into pages and bring them into main memory frames. The page table acts like an index, telling us which page number is stored in which frame address. When the CPU generates a logical addresses containing page number and page offset, we need to map it in the physical address in the main memory. Here is the performance issue. Both the pages we want and the page tables that locate them are stored in main memory. If accessing main memory takes X time, then first we access the page table, time is X, then we access the actual page, time is also X. Now the total time is 2X. This becomes worse with multi-level paging, where we might need to access multi-page tables levels, all stored in main memory. TLB solution. TLB is essentially cache memory, faster than RAM, where we store frequently used page table entries. The process now becomes CPU generate logical address. First, check TLB for page to frame mapping. If found, TLB hit, directly access the frame. If not found, then TLB miss, go through normal page table lookup. Now, the effective memory access time formula is TLB hit case, TLB access time plus memory access time. Now, in TLB miss case, TLB access time plus page table access time plus memory access time. Now total effective time is equal to hit ratio into hit time plus miss ratio into miss time, where hit ratio plus miss ratio is equal to 1, miss ratio is equal to 1 minus hit ratio. Now let's understand this formula with numerical example. Let's apply this formula. This question has been asked in GATE exam. TLB access time is 10 nanosecond, main memory access time is 50 nanosecond, TLB hit ratio is 90% and no page fault occurs. So what will be the solution? Now hit ratio is what? 90%, so it will be 0.9. Miss ratio is what? 10%, it will be 0.1. Hit time is what? 10 plus 50, it is equal to 60 nanosecond. Now miss time is what? 10 plus 50 plus 50, which is 110 nanosecond. Effective memory access time 0.9 into 60 plus 0.1 into 110, it is equal to 54 plus 11 is equal to 65 nanosecond. So this is the effective memory access time, which will be 65 nanosecond. Now important TLB concept. TLB has limited size due to cost constraints. We can't store all the page tables entries in TLB, so we store only the most frequent used ones. The effectiveness of TLB depends on having a high hit ratio. If the hit ratio is low, TLB actually hurt like performance because we are adding extra TLB access time without getting the benefit. This assumes no page fault occur. If the requested page isn't in the main memory at all, we need additional page fault service time to bring it in from secondary storage. Now moving forward to segmentation. Let's understand segmentation, which is another memory management technique where we divide processes into segments and place them into main memory. Paging versus segmentation. What is the key difference? The key difference lies in how we divide the process. Paging divides a process into fixed size pages without considering the program's actual logic. Now for example, if you have an addition function in your C program, paging might split this function across two different pages, placing part 1 in frame 3 and the part 2 in frame 4. This creates a problem. When the CPU executes the addition function, it gets partial code from F3, then must immediately fetch the rest from F4. This can lead to page faults and insufficient execution. Now how segmentation works? Segmentation works from the user's perspective. Instead of blindly dividing the process, it creates segments based on program's logical structure. Like we can say a main function becomes one segment, addition function becomes one segment, subtraction function becomes one segment. So each segment contains logically related code that should stay together. Unlike paging, where all pages are all the same size, segment can have different size. The addition function might need only a few lines of code, small segment. The main function might need many lines of code, large segment. This flexibility allows us to keep related functionality together while efficiently using memory space. Now, when the CPU generates a logical address, it's divided into segment number, most significant bits, offset is least significant bits. Here's how logical to physical address translation works. CPU generates logical address with segment number and offset, use segment number to index into segment table and get base address and size from the segment table entry. Now here comes the important step. Verify that offset. If offset is less than is equal to size, then if valid, then physical address is equal to base address plus offset. If invalid, generate trap or interrupt, segmentation fault. So generate a trap because it is requesting data beyond segment boundary. Now what is the advantages of segmentation? Logical organization. The first advantage is logical organization. Segments correspond to meaningful program units, which is logical organization. Second is variable sizes, efficient memory utilization. Protection. We can set different permission for different segments. Sharing. Segment can be shared between processes. Segmentation provides a more intuitive memory organization that aligns with how programmers think about their code, making it superior to paging for certain applications where logical program structure is important. So that was the whole concept of segmentation, which is very important. So that's it for this video. We will meet in next video. Until then, bye bye.